We will be getting started in just a second. Well, welcome. My name is Vincent Giuseppe. I'm from Oak Ridge National Laboratory and a co-spokesperson of the Majorana Collaboration. I'm pleased to introduce this special seminar where we're going to highlight our final results, our broad physics program, and some initial results from a new search. This event is hosted by our friends at the Sanford Underground Research Facility. I'd also like to thank our sponsors at the NSF and the Department of Energy. We will have a time for Q&A at the end of the presentation. For that, you can type questions into the chat, into the Q&A rather, and we can answer them from there, or you can also raise your hand and you'll be unmuted to ask your question. With that, I'd like to introduce our speakers for today's seminar. Ralph Mazarchek from Los Alamos, Clint Wiseman from the University of Washington and SEMPA, Anna Wren from UNC and Tunnel, and to get us started, Ian Gwynn from UNC and Tunnel. Ian, go ahead.
All right, thanks a lot, Vince. So we'll be talking about the final results of the Majorana Demonstrator. Next, please. So I'll begin by giving an overview of Majorana and of our final neutrinoless double beta decay result. Next. So neutrinoless double beta decay is a process that has never been observed before that converts two neutrons into two protons, two electrons, and no neutrinos. This is something that allowed if the Majorana is its own antiparticle, which is called being a Majorana fermion. If the neutrino is its own antiparticle, that enables the exchange diagram that's shown in this figure here, in which case the neutrino effectively annihilates itself. This would be direct observation of lepton number non-conservation, which has also never been seen before. And this would potentially provide a mechanism for understanding the excess of matter over antimatter in the universe. The detection signature for neutrinoless double beta decay is a peak at the end of a broad two double beta decay spectrum. So the broad spectrum is because of the neutrinos carrying away energy without interacting. But with no neutrinos, you get a monoenergetic signature, which we see as a peak. In germanium in particular, due to the excellent energy resolution, you see a very clear peak in an unambiguous detection signature. Next. So to search for neutrinoless double beta decay in germanium-76, we use high purity germanium detectors. So current experiments have limits on the order of 10 to the 26 years, which were achieved by achieving quasi-background free measurements, meaning on the order of one or less counts over the lifetime of the experiment with about 100 kilogram years of exposure. And both of them observed on the order of a few dozen kilograms of germanium for about 5 years. So on the right here, you can see the detection sensitivity as a function of exposure. And you can really see the importance of having a background-free measurement, which is required to get this straight line increase in sensitivity as a function of exposure. And you can see here that even small amounts of backgrounds can cut into your sensitivity. So achieving low backgrounds has been a very large emphasis for these experiments. So germanium detectors have many advantages for this, and as a result, they have a very long history of neutrinoless double beta decay searches. So germanium detectors are used broadly for radiation detection applications, which means it's a very well understood technology. The detectors can achieve very high detection efficiency by building them out of isotopically enriched germanium. They have very low intrinsic backgrounds due to the clean manufacturing processes, and they have excellent energy resolution and background rejection capabilities, which I'll describe later. Next. So that brings us to the Majorana Demonstrator, which is searching for neutrino subbeta decay germanium-76 using an array of high-purity germanium detectors. The experiment is also searching for additional physics beyond the standard model, which you'll be hearing about soon from Clint. And it also is seeking to develop the techniques that will be used in future experiments. So the experiment consists of two modules of detectors, which is to say an array of detectors inside of a vacuum cryostat. There's 30 total kilograms of detectors that are enriched to 88% in germanium-76, along with a handful of natural isotopic abundance detectors. The experiment achieved very low backgrounds by using a compact shield consisting primarily of copper and lead, as well as a muon veto, and the experiment was housed at the 4850-foot level of surf. So the experiment reached an ultimate sensitivity of 65 kilogram years, and we recently published a result with that, which I'll be talking about here. Next. So on this slide, you can see the full collaboration list. This is an international collaboration primarily located in the US. Next, please. And here you can see a photo of us that was taken at our first in-person collaboration meeting since the pandemic. Next. So now I'll provide a brief history of the operation of the demonstrator. So Module 1 was installed in 2015 and operated nearly continuously for about 6 years. Module 2 was installed in 2016. We operated it for a few years before upgrading it, in particularly by installing some inverted coaxial point contact detectors, which I'll talk about later. Both modules stopped operation in March 2021. The enriched detectors were removed and sent to Gran Sasso National Laboratory for inclusion in the LEGEND experiment. Since then, we've been continuing to operate Module 2 with only natural isotopic abundance detectors. And right now, we're performing a search for the half-life of the tantalum-182 metastable state, which you'll be hearing the first results of from Ralph very soon. Next slide, please. So now I'll talk about the strategies that Majorana used to achieve very low backgrounds. I don't have time to cover all of them, so instead I'll focus on the copper that we use. So the copper we use is the cleanest copper in the world. It was grown through the electroform processing process underground at surf and never allowed to see the surface. So in the top right, you can see the electroforming bath as well as the cleaning procedures we use for the surface. In order to avoid cosmogenic activation, we actually machine the parts underground. You can see a photo of the machine shop in the middle here. And in order to avoid radon exposure, we keep the parts in nitrogen-purged environments as much as possible, which you can see in the picture on the left. And this copper is then what we use to build the structure of the experiment, which you can see in the bottom right. Next slide. So the experiment also had the best energy resolution of any neutrinoless double beta decay search to date at 0.12% at the endpoint. So the energy resolution was achieved by using a novel ADC nonlinearity correction and a charge trapping correction that adjusts for the drift time of charge inside of the detectors, both of which were developed for the experiment. We calibrated the detectors using a thorium-228 line source. You can see the track, the plastic track that wraps around the module in the bottom left. And on the right, you can see what one of our calibration spectra looks like, with the dominant feature being this 2614 keV thallium peak and its Compton continuum, as well as a handful of other peaks from that decay chain. I'd like to particularly highlight two recent papers. So one was recently accepted by PRC describing our charge trapping correction, and another which will be submitted very shortly describing the analysis procedures we use to perform these calibrations. Next. So now I'll talk more about the types of detectors we use, which are p-type point contact detectors. So this describes the detector geometry, which has a point-like contact at the bottom of the detector, and then the outside N-doped, N+ contact on the outside. So the advantage of this geometry is that it produces a slow charge drift through the detector with a rapid rise as the charge approaches the point contact. And you can see that in the animation on the right here. This has advantages for pulse shape rejection that I'll describe shortly. So we use three different types of p-type point contact detectors. The PPCs and VEGGIEs are older detector technologies, and the newer one, which was developed for the LEGEND experiment, is the inverted coaxial point contact detector. What's special about these detectors is that they have much larger masses, which is nice for achieving lower backgrounds. And we tested 4 of these in the Majorana Demonstrator during the last year of operation. Next, please. So one of the ways we were able to take advantage of the p-type point contact detectors is by looking for multi-site events. So neutrinoless double beta decay is a single site event, meaning the charge deposition is located within about a millimeter of the site of the decay, while many of our backgrounds, particularly Compton scattered gammas, will happen at multiple sites inside of the detector. So because of the position-dependent signal that we see in p-type point contact detectors, multi-site events can produce signals like the one on the bottom left, where you see multiple distinct rises in the waveform. And we can recognize this by comparing the current amplitude to the full amplitude of the waveform, which we call A versus E. This is something that we've been using for since the beginning of the experiment, but new to our recent publication is an improvement in the uniformity, stability, and signal acceptance of this, which we were able to achieve using a specially designed cobalt 56 calibration source. Next slide, please. So the other types of events that we try to cut are surface events. So events, particularly from alphas and betas, will be located on the surface, while neutrinoless double beta decay is predominantly in the bulk of the detector. And in the detectors we use, the surface events have different signals than the bulk events. So for example, if you look at the flat top of the waveforms on the left, events on the black passivated surface of this diagram will often have a slope there instead of a flat top. And we call that delayed charge recovery, or DCR. And we've been cutting events based on that since the start of the experiment. New to this recent result is the improvement of 2 new discriminators. So one is to look at this very, very sharp rise at the start of the waveform, highlighted in blue, which we use the same A versus E discriminator, but we use a high cut instead of a low cut. And the other is to look for a slower turnaround at the top of the waveform, which is in this red rectangle. And that we call the late charge, or LQ discriminator. Next. So finally, before I get to the result, I'll talk about the inverted coaxial point contact detector. So as I said before, the advantage of these detectors is that they're much larger than the others, which is nice for achieving lower backgrounds. However, because they're larger, they have a much larger range of drift times, which can actually act as a confounding variable to many of our background rejection cuts in our energy calculation. So we had to actually refine our analysis to achieve the same performance in the ICPCs as the PPCs. But in doing so, we were able to achieve comparable performance. So on this slide, I'm showing the energy performance on the bottom. So on the left, you can see the improvement in the peak resolution of our 2614 keV peak that we achieved by applying this refined analysis technique. And on the right, you can see the full with half max curve. Next slide, please. All right, so with all of that, this is the final result of the Majorana Demonstrator. This was published about 2 weeks ago in PRL and includes 65 kilogram years of exposure. So here you can see the full background spectrum that we collected with the experiment. The dominant feature of the spectrum is the 2 neutrino double beta decay broad spectrum. And then in blue, you can see where it is that we search for a neutrinoless double beta decay peak. You can also see the effects of the background rejection cuts in this. So going from the black to the gray lines, you can see the effect of our surface cuts, which remove the vast majority of events near the end point of the decay. And going from the gray to the red, we remove about half of the remaining events using the multi-site event cut. And in doing so, we were then able to achieve the second lowest background index of any neutrinoless double beta decay search to date at about 16 counts per full with half max ton year. Next slide, please. So using this, then we were able to calculate this result. So we expected 1.5 background counts in our region of interest, and we measured 1 count, which means we saw no signal as expected. So we achieved a frequentist limit of 8.3 times 10 to the 25 years. When we convert this to the M beta beta parameter, which is the effective neutrino mass, and this is what's used for comparing different experiments using different isotopes, we achieve a limit of 113 to 269 millielectron volts, with that range depending primarily on theoretical uncertainties. And then this plot here, you can then see a comparison of the M beta beta limits for Majorana and other experiments, as well as a comparison between this and the allowed values for the M beta beta parameter based on other measurements. Next slide, please. So finally, I'll talk about the next steps for searching for neutrinoless double beta decay. So Majorana was able to achieve this excellent result using the techniques I described. Another experiment called Gerda was able to achieve an even lower background index, the best background index of any experiment to date, also using high purity germanium detectors. The way they achieved this was by putting their detectors in a liquid argon active shield. So the liquid argon scintillates when events pass through it, which allows them to actively reject backgrounds. And this was extremely effective for them. So in the future, we can actually combine the techniques developed by Majorana and Gerda, which are complementary, meaning that they're going to be able to achieve a better background index than either experiment individually achieved. This is the collaborations into the Legend collaboration, which is to deploy a bigger experiment in 2 phases. So right now we're collecting data with 200 kilograms of detector with Legend 200, and in 10 years or so, we plan on an even bigger experiment using 1 ton of detectors. So Majorana is also still not quite done, and the next steps for that is to build a background model, which you'll be hearing more about from Anna. Thank you.
Thanks, Ian. Next. So to introduce the topic of background modeling in the Majorana Demonstrator, I want to start with the same plot that you already saw before from Ian. This is the demonstrator's enriched energy spectrum with 65 kilogram years of exposure. And in the context of setting a half-life limit for neutrinoless double beta decay, all we really needed to know from this plot was the background projection in that really small 10 keV dark blue signal region. And to do this didn't actually require any kind of complicated background modeling. If you look in the light blue background estimation window, which is also shown in the inset, you can see that our background post cuts is actually very flat. And this means that we were able just to measure the rate in this background estimation window and use it as a proxy measurement for the background rate at Q beta beta. And in doing this, we got that number that Ian mentioned of around 16 counts per full width half max ton year. And although this measurement is a very low background index, it is still actually significantly higher than our assay-based projection of about 3 counts per full width half max ton year. And in order to understand the reason for this discrepancy, this is where we have to do more complex background modeling and look across a wider range of energies. Next. So this sets one of the goals for background modeling, which is to really locate the source of our background excess near Q beta beta. And one thing that we were able to determine about this really early on was that this background seems to be dominated by events from the thorium-232 decay chain. One of the reasons that we know this is that the 2615 gamma from that same decay chain is also underpredicted by the assay-based model. So that tells us what decay chain is causing our background excess, but it doesn't answer the question of where in the experiment that excess radioactivity is located. And so that is a question that we have put in a lot of effort towards working towards answering. And in particular, we want to know if the region that the background is located in could pose any issues for the next generation Legend 200. Next. So you may ask what kinds of backgrounds would cause issues for Legend 200. And the short answer is that if our background excess was due to something in this near detector region shown in blue within the cryostat, this could potentially pose issues for Legend. Now, it's important to note that with the exception of the germanium detectors themselves, nothing from this near detector region is going to be directly reused in Legend. But some of the low background materials and component designs have inspired some similar materials and designs in Legend. So for instance, that underground electroformed copper that is electroformed at surf is being used in Legend 200. And also the front-end electronic design that helped achieve the very good energy resolution in the demonstrator was slightly modified and is also being used in Legend 200. And so it has been important to us historically to determine how much of our backgrounds are coming from this near detector region, so we can understand whether these parts could pose issues for legend. Next. Now, this is not the only goal of background modeling. Another thing we want from background modeling is to measure the 2-neutrino double beta decay half-life. And this can be done. You can see that this is the dominant feature in our spectrum, is this 2-neutrino double beta decay spectrum. But to get a really good precise measurement here, we need to understand the contributions in this energy range from other background sources so that we can subtract those away. Next. And then, of course, in general, it's good for a number of different physics analyses to have a comprehensive background model over a wide energy range with well-quantified uncertainties, so that you can use it in searches for other physical processes, specifically beyond the standard model physics. For example, what you can see by looking for deviations in the 2-neutrino double beta decay spectral shape. Next. So in addition to what we can determine by looking at just our energy spectrum over all enriched detectors, we can also look at the spatial distribution of our backgrounds to determine something about where they're coming from. And what we see when we do that is that our background in module 1 is actually about a factor of 2 higher than our module 2 background. And we can actually get even a little bit more granular than this by looking at things detector by detector. In this case, our statistics become a little bit more limited. But there are still some interesting things we can observe. And the main one is that the 2 detectors nearest to the module 1 cross arm show significantly elevated rates compared to the other detectors. These 2 detectors are natural detectors, so they're actually not directly contributing to that background index number, that 18.6 number. But they do help us to understand where our backgrounds are coming from, and some of the enriched detectors nearby show more modest elevated rates. So these 2 hot detectors are not only a high rate in the background index region, they're high rate over a wide energy span, and then also in particular in prominent energy peaks from the thorium decay chain. So on the heat map on the left, you're seeing that for that 2615 keV gamma. But this is also true if you look at a low energy gamma, such as the 238 keV gamma that's shown on the right-hand plot. So this plot is comparing in pink one of the near cross-arm detectors with the other natural detectors from the module, which are across the cryostat from it. I'll just make a quick note here that the other near cross-arm detector has lower statistics because it was biased down partway through. So while we're able to determine that it does have elevated rates, the rates in particular peaks are less clear, which is why it's not included on this plot. So this tells us that our background isn't really something that is dominated by a uniform contribution from near detector components. So it's not like all of the front-end electronics are hot. And we've also been able to do some studies with peak ratios to determine that this isn't related to, for instance, a single hot front-end electronics piece near one of these detectors. Next. But to get more nuanced than that, we really have to start doing comparisons between simulations and data. So our simulations are Monte Carlo based, and they're fairly complex, or detailed rather. There's around 4,000 simulated parts. And when we're generating primaries, we combine those parts into around 27 different component groups. And we simulate up to 9 different decay chains in each component group. Some decay chains are only in a couple groups. And from there, we end up with around 100 simulated PDFs that get floated during our fitting process. We do have both a frequentist and Bayesian fitting program. Our frequentist fits are what I'll be focusing on for this talk. And in our frequentist fits, we're looking at the energy range above 100 and going through that full region covered by the thorium decay chain up to above 2615 keV. And the data that we use is the demonstrator's data with only some minimal data cleaning cuts. And then we also actually do one of our surface event cuts, our DCR cut. And the reason for that is that we don't have a good simulated model for the surface alphas because of their energy degradation effects that we're still understanding some of the physics behind. Next slide, please. So before showing results of fits to data, or some initial fits to data, I'm going to talk about some fits that we've done to simulated data sets to understand the conclusions that we'll be able to draw at the level of statistics that we have. So the reason that these simulated data sets are useful is they're produced by summing different simulated PDFs weighted by predetermined activity values. And since those values that are used to build the model are known, we can test how well the fitter is able to recover those true parameter values. So we've done this in a number of test cases. We did some initial tests at high statistics simulated data sets, and then determined from there that we were able to very precisely pick out the parameter values that we put in, which gave us some good faith in our fitter. And then we've also done some tests at a level of statistics more akin to the demonstrators, where low statistics makes the problem a little bit more complicated. And one of the conclusions we've drawn from that is that we're able to measure the 2-neutrino double beta decay half-life with a low statistical uncertainty. Next. A somewhat more nuanced study that we've done with these simulated data sets is to try to determine how precisely we're able to locate the region of the demonstrator's excess. And to do this, we use simulated data sets where most components were at their assay-based activity values, but in one or two components, we put in elevated thorium that was scaled to match the thorium rates that we see in data. And then we performed fits to these data sets. So at this plot on the left, you see an example of this where we had put elevated rates in our cables along the crossarm in both module 1 and module 2. And the counts in the model are what's shown in black. And then we tried to fit this out. And so the green is showing the fit results with the error bar showing the deviations over 50 different trials. And you see from the size of the large error bar that we're not able to precisely locate this component in a single fit. And this is partly because you see there are some other components that also have large error bars. And these are some fairly highly correlated components, like the connectors that are above the cold plate. But what you can do is you can combine counts from component groups that are located close in the experiment to one another. And when you do that, you go from the plot on the left to the plot on the right. And the plot on the right, what this is telling us is that we are able to really conclusively say what region of the experiment the excess is in. So while we might not be able to locate it to the cross-arm cables, for instance, we can say conclusively, even at this low level of statistics, that it comes from the middle region rather than a near detector component or something further away like the lead shield. And this was very reassuring to us because it tells us that we should be able with our data to answer one of these main background model goal questions that we have of what region in the experiment the thorium excess comes from. Next. So I'll also show here some results from some initial fits to a subset of our open data that we did a while back. In the next couple of months, we hope to have fits to our full set of our full exposure. These initial fits to a subset of data support some earlier studies that we had used, looking at things like low energy to high energy peak ratios. And what their data is mainly telling us at this point is that our background excess seems to be dominated something from the middle region, which is what is shown in purple in that bottom right-hand plot, and then specifically the middle region of module 1. And this includes that cross-arm area that we expect to have somewhere in it some elevated rate based on what we are seeing from our detector distribution. We've done some ongoing assay measurements that have allowed us to rule out certain components in that region as having high enough activity to be responsible for the excess. But work is still ongoing in that direction. And when we publish our full exposure model, we hope to kind of have this result with well quantified uncertainties for systematic effects, like, for instance, the shape and thickness of the dead layer. Next. So the demonstrator achieved very low backgrounds, and we've been making very good progress towards understanding where those backgrounds that we do observe originate from. And we've been able to determine that they don't appear to pose a problem for the next generation Legend 200 experiment. Now, this background model fits, as I mentioned earlier, started around 100 keV. Below this range, we have to use more complicated data cleaning cuts to be able to understand our data well, but there's been a lot of really good physics analyses that have been done in this region, and that's what Clint's going to talk about with you now.
All right, thanks, Anna. I appreciate that. So I'm going to talk about our search for beyond standard model physics and dark matter with Majorana. So Ian and Anna showed you the full energy spectrum of the demonstrator, really focusing on that area at 2 MeV. And I want to show another place where Majorana is really interesting, which is what we call the low energy spectrum. And that's sort of the data between about 100 keV on down to about 1 keV. And I'm showing the two sets of detectors that are installed in the demonstrator. And one thing you can see right away is the effect of really carefully keeping track of the amount of time that the enriched material spent on the surface. So in black, you see the spectrum from the natural detectors. You see a really sharp cosmogenic line, germanium-68, iron-55, and this big continuum from tritium. These are isotopes that get activated when the detectors are on the surface. And Majorana went through a long process of trying to carefully control the amount of surface exposure that these detectors saw. And so the enriched material is showed in the red spectrum here. And we can see germanium-68. We can also see some lead-210, actually in both of, at a similar rate in both natural and enriched. And we also see this kind of interesting feature where the enriched spectrum sort of seems to curve up at lower energies. So I want to say that the Majorana Low E program is really dependent on kind of 4 important aspects. It's the ultra-low backgrounds that we work so hard to achieve. There was a lot of effort during designing construction to optimize the electronics readouts and allow us to take this very low signal-to-noise data. There were some studies pre-Majorana, Malbec and Cogent, which showed how important it is to reject the surface backgrounds, especially at low energy. And I'll talk a little bit more about that. And we also spent a bunch of time developing advanced data cleaning techniques. We did a lot of waveform fitting, wavelet denoising, and all of that stuff. And at the end of the day, we're left with this spectrum, which is sort of a probe for a wide variety of physics beyond the standard model. And I'm going to kind of try to talk about this new frontier in sensitivity to these fundamental physics signatures here. But first, I have to talk about how hard it was to clean up the data set. So like I said, we applied waveform fitting, wavelet denoising, and a whole bunch of other things. You can see our raw spectrum here in black. And at the lowest bin here, we achieved something like a 5 order of magnitude noise reduction. And this is with known efficiencies, typically computed from calibration data. So we're quite proud of this. There's all kinds of things we had to reject: unstable baselines, high frequency chirps, slow pulses, which are surface events from the N+ dead layer. The low energy data set is just a little bit different from the primary data set. We start at the same spot with the commissioning data in June 2015, and then the low energy data set cuts off at November 2019 when the modules were removed to install the new ICPC detectors. And there's a lot of physics you can do with this, so I wanted to throw up some of the papers that we've published here. So in addition to the primary neutrinoless double beta decay search, we can look for all kinds of crazy things like baryon number violation, violations of the Pauli exclusion principle, or wave function collapse. These are things which are taught in undergrad quantum mechanics, and they may actually have detectable signatures if they're violated in a small way. There's all kinds of dark matter we can look for. Typically they make a peak in the low energy spectrum, so I'll talk a little bit about how we try to find that. And there's also a variety of other background studies we can do with this data set as well. So this, the excellent energy performance and the low backgrounds in this data set really enables a lot of physics to be done. It complements the main double beta decay search. And I also want to highlight something we're pretty proud of this year. We've made the cover of PRL. The plot you're seeing here, I'll talk a little bit more in a second here about. But in this article, in this edition, we were able to get 2 articles. A search for spontaneous radiation from wave function collapse, which is a test of quantum mechanics, and also a search for solar axions. So I'll talk about that first. We were able to set new limits on the coupling of solar axions to photons. And basically what's happening here is solar axions are expected to be produced in copious quantities in the sun via the Primakov effect. They travel through from the sun to the Earth through the mile of rock of surf down to the demonstrator, and they can convert back into photons and cause ionization by the inverse Primakov effect. So this pretty picture that PRL highlighted is actually the change in the rate that you see as a function of the day as the Earth goes through an orbit. So the axions are a little bit more likely to interact when they sort of line up with the crystal axes of our detectors, and it produces this really pretty but also kind of hard to analyze time-dependent PDF. So our analysis here is dependent on the energy of the signal, but also has this really complicated time dependence. So we take a 5-minute precision over a 3-year data set, and of course ultimately find the solar axion flux is consistent with 0 within 2.2 sigma. And that allows us to set a limit on the axion-photon coupling, which I've shown here, which surpasses the previous lab-based limit for 21 years, which was work by Dama in this 1 to 100 EV mass range. KeV, yeah, EV, sorry. Another thing which I mentioned here is a search for wave function collapse. So this has been talked about for years. This is sort of the quantum measurement problem. And people have been asking things like, where is the border between the microscopic and the macroscopic worlds? How does the wave function collapse when a quantum system interacts with its surrounding? One of the theories that has been proposed is that the wave functions are sort of continuously, spontaneously localized. And the important thing about this proposal is that it makes a detectable signature that we can actually test. What's supposed to happen is that the atom is sort of spontaneously localized, collapses down, and then goes back and emits a low energy X-ray. And the energy of this X-ray, it sort of follows this 1 over E distribution. So the plot in the middle here I'm showing is the contribution of that signature to the low energy spectrum. It's a fit. We don't find a significant signal again, so it allows us to set new limits on this continuous spontaneous localization theory. And we did get a little bit of press too. Quanta magazine wrote about us, and I also think that the community in general is kind of interested in this. There was an article by Sean Carroll in Physics Today, which sort of talks about this quantum measurement problem. So again, the continuous spontaneous localization isn't the only theory of wave function collapse, but it is testable. So we really chose to focus on that. We've also been looking in this low energy region for rare peaks from exotic dark matter. I've shown 2 examples here. There's a whole lot of dark matter models that are alternative to WIMPs. Many of them would produce a sharp peak in the low energy region in germanium detectors. So that includes axion-like particles, dark photons, which are both examples of bosonic dark matter. Recently, there's been some more interest in theories of fermionic dark matter. There have been results by Panda X, XO200, and a few others. But the strategy is pretty much the same. The dark matter particle comes in. For bosonic dark matter, it interacts with the electron. The entire energy of the dark matter particle is absorbed, and then it creates a peak more or less at the dark matter mass. Similarly, for fermionic dark matter, you have one coming in. It interacts with the nucleus, and a neutrino goes out, but that also produces a peak at a well-defined energy. So what we do is basically a bump hunt. So we scan across the low energy region, looking for a rare peak, which you can see in purple here, taking into account all of our various cosmogenics. Our germanium-68 line is pretty prominent. And if we don't find a peak which has a strong local significance, probably more than 3 or 4 sigma locally, then we go ahead and set a 90% upper limit on the number of counts that you could possibly attribute to this dark matter signal at this particular energy. So for a lot of our work, what we end up doing is setting upper limits for these various models. So I just wanted to throw up a couple of these plots here. We've set exclusion limits for fermionic dark matter. We've looked at the sterile neutrino transition magnetic moment. We've looked for bosonic dark matter, both the pseudoscalar axion-like kind and also the vector dark photon kind. And I also want to highlight another one of continuing our search of quantum weirdness with Majorana. What I've shown here are sort of 3 processes that are not allowed by quantum mechanics, which would nonetheless produce a detectable signature in the demonstrator, which we can look for. So a theory of charge non-conservation, one way you could look for it is that an electron on the K shell spontaneously decays to either 3 neutrinos or 3 dark matter particles. And there's also a couple of different mechanisms of violation of the Pauli exclusion principle that we can look for as well. We think we've got a competitive result here, and it'll should show up in the archive before too long. Actually, I believe it is on the archive. You should see it in the journal before too long. So just a couple of takeaways to re-emphasize. We've got really low cosmogenic activation for the enriched detectors, and that was a big effort to get that way. We've got excellent energy resolution and 1 keV thresholds. That's a testament to the hard work of developing the readout electronics and calibration. So it puts us in a really good spot to look for all kinds of beyond standard model physics at low energy. Again, I've highlighted these solar axions, dark matter. We've also looked for lightly ionizing particles and other things as well. And the results from these low energy searches can also inform the next generation of beyond standard model searches. We're already looking at what we might be able to do with legend. And yeah, we're just looking forward to the next chapter. So last, I'm going to pass it to my colleague Ralph, who's going to talk about the next study.
Thank you, Clint. So I'm going to finish the overview and the results with our newest search, and therefore we switch gears a little bit. So the physics we are investigating at the moment at the demonstrator facility is a little bit different, but also is almost 100 years old, or even a little bit further. And it is the physics of isomers. Isomers are usually isotopes which we can identify that they have the same atomic weight. They also have the same chemical character, but they actually act differently when they decay or how stable they are. And what people found out like 100 years ago and predicted is that actually the spin of the nucleus is the important quantity. Today we have found isomers which are very short-lived and very long-lived, and I'm going to show you in the last few minutes a very, very long-lived decay we are trying to find. Just to give you an easy picture about what isomers, where they play a role. In principle, if you excite an atom for whatever, like with different mechanisms, it works kind of like a kid on a swing. You just put some energy in the system, you excite it, and in the best case, it de-excites, the kid comes back and actually can go home at some point. But of course, if it goes wrong, then you're kind of stuck somewhere in between. And this is actually explained by so-called spin traps. Like I said before, the theory is actually talking about spins. And one of these isomers that can have such a spin trap is tantalum. Tantalum, unfortunately, is not the easiest case to investigate because it's actually one of the rarest materials in the solar system. So if you plot the abundance of the different materials in the solar system, tantalum is orders of magnitude less than like more common materials. And in tantalum itself, 99.98% is actually on the wrong isotope. So the isotope we are interested in is 180 tantalum. And here the ground state is actually decays within 8 hours, but the isomer itself is what we call metastable. It's very long-lived, and it exactly fulfills the prediction from 100 years ago. It's actually the only long-lived occurring isomer in nature. So why do we do this? Because we want to test this very basic physics. It's really traditional nuclear physics, but it's on a really extreme scale. So we can really look for tiny effects and deviations from this classic physics. So how does tantalum actually look like, and how does this scheme look like? So in tantalum, we are in this excited state. We describe it by spin and parity. In this case, it's a 9- state. And this state can either decay to the ground state. That's kind of like what I showed you before. The kit just goes straight back to the middle point. And then this ground state will decay. So in our experiment, we, for example, would look for this decay and see if we see some of these signatures down here from the neighboring isotopes. What also could happen is that the isomer itself decides not to go to the ground state and straight goes to the neighbors. In this case, the physics describes us where we can go, and what we actually would see would be cascades of gamma rays. So we go in these higher spin states, and they cascade down to the ground states. So when we look in our demonstrator data, which we're currently taking, we would look for signatures where we have this higher energy gamma rays or even multiple gamma rays. And then, of course, this physics can be also extended to more like beyond standard model physics. You could imagine that you're stuck in this state and now a dark matter particle comes along and somehow helps you to overcome this problem, and the dark matter actually pushes it out of the isomeric state. So in this case, we would look like a very similar signature as before, but it's induced by dark matter. Just a little bit of history. If you look at when people started looking for tantalum, it actually started like in the 1950s already, when the first gamma detectors came out. And they set the first limits, which are roughly the age of the universe. And the most current data is going up to 10 to the 17 years. This is, of course, a little bit shorter than double beta decay, but it's still a very extreme case. And in a few more slides, so be patient, I'm going to show you where we stand. So what is actually needed for a good measurement? First of all, of course, a lot of tantalum, which is, of course, a problem since it's such a rare material. Then you need a detector with an excellent energy resolution because you're chasing after these gamma rays. If possible, you also want to have multiple detectors because you want to detect these coincidences. And And of course, you don't want to suffer from a background, so the best thing you can have is actually an ultra-low background system and environment. So this was actually the perfect use of the Majorana facility after we removed the enriched detectors last year. Just to give you some impressions how this looks like actually in real life. So we bought tantalum, we bought very pure material. And this tantalum came in these discs you see here. We followed all the Majorana standards for cleanliness whenever we introduce a material into our system. So this tantalum was actually cleaned and pumped and baked. And at the end, it was installed between the germanium detectors. Here's some pictures from when we actually did the work. So you see this germanium crystals, and on top there's some tantalum discs stacked there, then the next germanium detector, and you start building these towers or strings of detectors. If you look at this at the final module, this is like the second module that you saw before. Now just with natural germanium detectors and the stacks of tantalum in between. In total, we installed about 17.4 kilogram of tantalum. If you calculate how much tantalum 180 this is, it's only about 2 grams. So all this effort was just to actually get 2 grams of tantalum 180. We have 23 active detectors. And as you see, these detectors are stacked here in a certain pattern, which is actually to maximize the detection efficiency. We're taking data as of May last week, and what I'm going to show you today is actually the first data release, which consists 229 days of data. Out of this 229 days, actually 225.5 days were really good tantalum data. The rest of it was calibration or short shutdowns. So how does the data look like at the end? What you see at the end is a spectrum like this, where you have the energy and you histogram all the events, how often they occur in the time. What I see in my spectrum is that, first of all, I have very low contributions from natural radioactivity, which is a good news because this means we make perfect use of the Majorana Demonstrator facility, which had a very low natural radioactivity, but also that our samples are very clean. What I also see is that there are examples from cosmogenic activation. The tantalum, of course, was produced by a company which is on the surface, and certain isotopes like 180 tantalum or 175 hafnium are created on the surface and very slowly decay away. So if I look at my data as a function of time, you actually see that our background is improving as we're speaking. And now, of course, we come to the most important plots, which are I show you 2 examples here. So our data looks at the end. We have the spectrum as a function of energy, as you saw before. This is kind of a zoom in. We blind our data with you see the black data here has spots where we don't look into. This is what to aim, or we try to build all the mechanics to analyze everything before we actually look in our box and try to understand the spectrum before we analyze our results. So what you see here, there is a components in the spectrum which come from the 182 tantalum activations, which can be fitted. There's a flat background in between. And then there's this region where I try to find the tantalum peak. And this is, of course, now the unblinding almost live, because I had needed a few days actually to make plots. So forgive me that it's not perfectly live. And so this is how it looks like. So I hope you see it now in gray here. You see the extra data. And what you also see in red is what the signal strength would look like, or where we set the limit at the moment. So we have the mechanics in place, and this assumes that at the moment there's a peak with a certain strength here. How does this look at the end in total numbers? And this is this table you've seen before, but now with our newest results. At the moment, all our results are still consistent with 0. The results what we have seen is that our background is actually comparable with all the previous efforts. And as I showed you, our background is even getting better. So this is one of the improvements we hope to achieve over the next year, that we actually get a much better measurement itself. What you already see is that our numbers are already about 2 orders of magnitude better than all the previous measurements. And this is mostly because we have a much better efficiency. I showed you the stack of germanium detectors and tantalum. We increased the mass of the tantalum. We have a huge number of detectors, where most of the older measurements had only a limited number of detectors. And like I said, our background is getting better. So just to summarize the effects, the measurements, we at the moment going to about 10 to the 19 years. You see this 2 to 3 orders better. And this is more or less the first time that an experiment achieved a half-life sensitivity for classic beta decays or electron captures that is beyond 10 to the 19 years. The only other experiments that reach this range are experiments that look for either very rare alpha decays or the double beta decays like Majorana itself. And then now, of course, it's not all bad news that we didn't see anything, but we still can learn something from the data. Because the fact that we didn't see anything means also that there was no dark matter which came in and interacted with the material. So we can, of course, look for different dark matter ideas that would interact with the nucleus. And I just show you here two examples, where one, for example, on the right one is where we have an inelastic dark matter, where dark matter comes in, interacts with the nuclear state, and then transitions into a different kind of dark matter. What we have done here is that we, like, at the same time where we improved the half-life limits, we also improved our understanding in the same dark matter and different dark matter models by the same orders of magnitude. And these searches are actually very complementary to other searches. So it's like even a null result in this case was an advancement in the field. So just to summarize it, the tantalum effort, this is the most sensitive search for a half-life measurement in an isomer worldwide. The first data I showed you today improved all the previous measurements already by 2 or 3 orders of magnitude. So we're going about to 10 to the 19 years. We estimate that the final sensitivity in all channels at the end will be around 10 to the 19 years. And this should have the potential to discover the decay. This, of course, was made possible by that we have this unique facility as SURF, that we had all the cleanliness procedures and the performance of the demonstrator, and of course by support by the LANL LDRD. Okay, with this, I hope over the last 50 minutes, our 4 speakers have shown you a summary of our efforts over the last 3 years. We have given you an overview of the Majorana and the final double beta decay results. So we achieved a half-life limit of about 8 times 10 to the 25 years and established different methods and techniques which are important for the next generation experiments. We did a number of studies and which are still ongoing to understand our radioactive background and where it's coming from. And we're developing a background model and trying to understand where the background is coming from, and so that we, for the future experiment, avoid these background sources. We have shown you that, like, these experiments, even they're looking for neutrinos double beta decay, have the potential actually to look for a whole range of physics of beyond standard model physics, including dark matter. And I've shown you that, like, that currently we modified the facility and make use of the excellent conditions to actually do a new search for different physics. And with this, I would like to thank all our sponsors, in particular the NSF, the US Department of Energy, the LDRD program, and of course our hosts here at the Sanford Underground Research Facility. Thank you. Oh, and maybe as a reminder, if you have questions, please put them in the chat or in the Q&A. And then we try to read them and then get them to Anna, Ian, Clint, or myself to answer them. Okay, let's start with the Q&A. The first question is, why are some detectors inactive?
I think we can give that to Ian.
Yeah, Ian?
Yeah, so there were a variety of reasons for detectors to be inactive. In some cases, it was problems with the electronics, either the high voltage or signal carrying electronics. That meant that we weren't able to get data from the detectors. In some cases, we also had detectors that we did not use the data for short periods of time due to instabilities in analysis parameters.
Okay, the next question more or less goes in my field. Is there a prediction for the half-life limit for 180 tantalum? And I hope you still see my screen.
Yeah, you got it. No,
if not, let me just talk you through it. Like, yes, there are, from theory, depending on the decay mode, some of them are very long-lived, tend to like up to 10 to the 31 years. The one which is the most promising and the dominating one is between 10 to the 18 and 19 years. That's when the isomer decays to the ground state, but via an internal conversion. And this should be within the sensitivity range that we can achieve at the end of the experiment.
Nice.
Can I add a quick comment to the inactive detector question as well?
course.
I did want to mention also that we did a cable and connector upgrade before removing enriched detectors, where we were able to show that some of these problems that were leading to inactive detectors were problems that we were able to fix. And so while this didn't contribute as much exposure, since it happened fairly late in the experiment, we were able to validate that we were able to find solutions to some of our cable and connector related inactive detector issues.
Yeah, right. Thanks.
Yeah, thanks, Anna. We've got a question from Hamish. To what do you attribute the low energy rise in the spectrum below 20 keV in the enriched detectors? And this is something that we thought about for a very long time, so I'm pleased to be able to give you at least a partial answer. So I think one of the clues is that we see lead-210 at more or less the same rate in the natural and the enriched materials. And that lead-210 is part of the mass-210 system. There's a bunch of different decays happening, a couple of which are emit betas. So a reasonable explanation is that what's happening is that not only are we seeing this, this gamma from lead-210, but we're also seeing the various electrons impacting on the passivated surface. And we also are fairly confident that it is not energy degraded events originating from the N+ dead layer. So that was something that the Cogent experiment and Malbec thought about a lot. And we didn't have time to really show the work here, but basically we were able to develop slow pulse cuts which reject energy degraded surface events that have a characteristic shape coming from the N+ layer. So we're reasonably confident that slow pulses are a minimal contributor. I won't say non-zero, but a minimal contributor to this rise here. And it seems at this time like it's most likely electrons coming out of this mass-210 decay chain system. We've got one for Ralph here. You want to read it?
Okay, the question is, how do you differentiate a dark matter-induced tantalum decay from a non-dark matter-induced one? At this point, the demonstrator can't do it. If we see a signal, I'm going to be modest and say it's classic nuclear physics, and I don't find dark matter. One advantage I have is if I see a signal with a certain strength, I actually can go into this, can calculate what kind of dark matter it would span and can, for example, compare it with other experiments. So as you see, for example, in the plot on the left, there is a certain region where the current data also overlaps with information from other experiments. So if I would see a signal which would speak against dark matter because it's excluded by other experiment, it's completely coming from nuclear physics. And if this is not the case, then I would usually I tend to be modest and say that that's expected from classic nuclear physics. But of course, there's like the whole community plays a role. So as soon as other experiments find a dark matter signal, you can reanalyze the tantalum data and can estimate how much comes from nuclear physics, how much is dark matter induced.
Great. I think the next one we probably want to kick to Ian here. Ian, can you see that?
Anna?
Or maybe Anna actually would be better. I'll go
Sure,
ahead.
yeah. This
Can you
is
see the question?
I can, yeah.
Okay.
So this is, did the thorium-232 decays explain well the excess of the background events observed compared to the rates expected from the assay-based model? So yes, thorium decays do a good job of explaining this background. We're just trying to determine where in the experiment those thorium decays would be located to best agree with a wide range of information we have from data about our backgrounds, both sort of the energy spectral profile, but also the rate of coincident events from different gamma peaks, and the detector distribution of our backgrounds.
And if you actually go back to our final background spectrum and just look at it, you can kind of, yeah, right there, thank you. So if you look at the region around the Q value, it really looks a lot like our thallium-208 Compton continuum, the 2614 KeV peak right where you expect it to be. Then you see the Compton shoulder also right where you expect it. So this is really consistent with the idea that the dominant feature in the background around the Q value is the thorium.
Another thing you can look at as well is if you look at the energy range above the 2615 keV peak, you'll see that after our surface cuts are applied, we see really very few events remaining after surface cuts in that region, which again shows us, is adding to the evidence that our backgrounds below that peak are related to sort of Compton scattering events from that same 2615 keV peak.
Okay, the next one is about how do we know the abundance of tantalum 180 in tantalum? Is there a measurement of the amount of 180 tantalum in the experiment? At this point, not. So when we bought the material, we assume it has the literature abundance. It also changed over the last few years. There's actually the abundance values has a certain uncertainty, so we will include this in our final results. At the same time, we are working actually on getting an ICP-MS analysis of one or two of the discs I showed you done to verify that this is close to the literature value, or if not, we actually have a measured value and can use this for the estimate of the half-life. The numbers I have shown you today are all under the assumption that the material comes from, agrees with like the natural abundance. Okay, then the next question I guess we're going to ask our spokesperson.
Yeah, he's going to take care of it.
Well, sure. The next question is, what will happen to MGD, Majorana Demonstrator, after the tantalum study? Are there any other proposals for future studies? What will SURF do with the Hall if and when Majorana is removed? Yeah, certainly a great question, and something we've been having good conversations with SURF management on. First and foremost, we want to get the best scientific output we can out of the tantalum, continuing the tantalum work, and we've made, I think we have a good case there. Beyond that, I think we're also having discussions with what science opportunities might come up given resources, but we also know that there's good competition, there's a good demand for the space too. So anyway, it's a bit early to say for sure, but again, something we're having good discussions with SURF management on.
One thing I would just add to that is, we've managed to make one of the most radiation quiet cubic meters in the world at SURF, thanks to their help. And so it's not too hard to think of cool science that you could do with such an array. Will any of MJD's data be made public? I think the short answer is yes. You probably don't want all of our waveforms, which are terabytes and terabytes and terabytes of raw data, but I think it's absolutely reasonable for our major data releases to, upon reasonable requests, make whatever available that people want to look at.
And I'll add that the final limit paper that just got published actually has a list of the events in the region as a supplemental. I imagine you're interested in seeing much more than that, and we do have a group within the experiment that's currently working on how will we preserve our data and how will we make it accessible to people. Sure.
All right, well, I think we've knocked down all the questions from the Q&A. If there's any more, go ahead and get them in. We'll give it a second if anybody's doing any last-minute typing. You want to wrap it up?
Well, if there's nothing else, certainly appreciate everyone's attention and joining us today. Thank you very much to our 4 presenters who did an excellent job. And I want to certainly, again, thank the collaboration and our sponsors and our friends here at SURF. So have a good evening. Thank you.